We see the surface, the non-stick wonder. But deep within a US lab, a chemist didn't just discover Teflon, he unknowingly activated a dormant element, altering the very texture of existence in ways we're still failing to comprehend. Welcome to a journey through one of science's most fascinating twists, the accidental invention that revolutionized kitchens, space exploration, and countless industries. Often, innovation springs from meticulous planning and years of dedicated research. But sometimes, the greatest breakthroughs arrive unannounced, born from a moment of curiosity, a keen eye, and a fortunate error. Today, we delve into the incredible story of a US scientist who, while searching for one thing, stumbled upon something entirely different, creating a material that would touch nearly every aspect of modern life: Teflon. Our story begins in the late 1930s, a time of rapid industrial growth and scientific advancement in the United States. The DuPont company, a giant in the chemical industry, was at the forefront of this wave, constantly pushing boundaries in material science. One area of particular interest was refrigerants. Traditional refrigerants like ammonia and sulfur dioxide were effective but highly toxic, posing significant safety risks. The world was crying out for safer alternatives, and chemists were diligently working to create new, non-toxic refrigerants, particularly the emerging class of chlorofluorocarbons, or CFCs. Enter Roy J. Plunkett, a brilliant young chemist. Plunkett had just earned his PhD from Ohio State University and joined DuPont's Jackson Laboratory in Deepwater, New Jersey in 1936. His assignment was clear: develop new CFC refrigerants. Plunkett's specific project involved researching a gas called tetrafluoroethylene, or TFE. He would synthesize large batches of this gas, store it in pressurized cylinders, and then use it for various experiments, hoping to find new compounds suitable for refrigeration. Little did he know, one of these cylinders held a secret that would change his life and the world forever.
The fateful day was December 14, 1938. Plunkett and his assistant, Jack Reebok, were preparing for an experiment involving tetrafluoroethylene. As was standard procedure, Plunkett retrieved a cylinder of TFE gas that he had stored the previous night, cooling it with dry ice. When he opened the valve, expecting the gas to flow out for his experiment, nothing happened. This was puzzling. The cylinder felt heavy, indicating it wasn't empty, yet no gas was escaping. Thinking the valve might be clogged, Plunkett removed it. Peering inside, he and Reebok found something truly extraordinary. Instead of compressed gas, the inside of the cylinder was coated with a strange, waxy white powder. It was unlike anything they had ever seen. The TFE gas had simply vanished, replaced by this mysterious solid. Many might have dismissed it as a contaminated batch or a failed experiment, perhaps even just an annoying mess to clean up. But Roy Plunkett was a scientist driven by curiosity and an innate desire to understand the why. He didn't just clean it out, he began to investigate. He carefully scraped out the white substance, which felt incredibly slippery and almost waxy to the touch. It was clear and pure, indicating it hadn't been mixed with other contaminants. The TFE gas had somehow polymerized inside the cylinder, transforming from a gas into this solid polymer. The iron from the inside of the cylinder likely acted as a catalyst, and the extreme cold from the dry ice played a crucial role in initiating the reaction. Plunkett had inadvertently created a completely new material, a polymer of tetrafluoroethylene. He had no idea yet of its properties or its potential, but he knew he had found something significant. This wasn't just an accident, it was an accidental discovery waiting to be understood.
What Plunkett had discovered was polytetrafluoroethylene, or PTFE. Over the next few days and weeks, he and his team began to systematically analyze this new polymer. The results were astounding. PTFE exhibited properties that were, frankly, almost unbelievable. It was incredibly inert, meaning it reacted with virtually no other chemicals. Acids, bases, solvents, nothing seemed to affect it. It was impervious to heat, resisting temperatures far higher than most plastics could endure without melting or degrading. Furthermore, it possessed an incredibly low coefficient of friction, making it one of the slipperiest substances known to man. It felt like nothing could stick to it. DuPont recognized the potential of this unique material almost immediately, despite not fully understanding how to manufacture it on a large scale or what its initial applications would be. The challenge now was immense. PTFE was notoriously difficult to process. Its high melting point meant it couldn't be easily molded or extruded using conventional plastic manufacturing techniques. It required specialized high-temperature sintering processes, similar to those used in powder metallurgy, which were unfamiliar to the plastics industry at the time. For years, PTFE remained a laboratory curiosity, a material with incredible properties but no clear path to commercialization. Scientists grappled with its intractability, conducting endless experiments to find a way to tame this miracle substance. It was too stable, too slippery, too inert, almost too perfect for practical applications using existing methods. The accidental discovery was one thing. Harnessing its power was an entirely different, prolonged battle. Little did they know, a looming global conflict would soon provide the urgent impetus needed to truly unlock its potential.
The breakthrough for PTFE came during World War II, driven by the intense demands of the Manhattan Project, the top-secret effort to build the atomic bomb. Scientists needed a material that could withstand the highly corrosive uranium hexafluoride gas used in the isotope separation process. This gas was so reactive that it corroded almost every known material. PTFE, with its unparalleled chemical inertness, was the perfect, indeed the only, solution. It was quickly pressed into service for gaskets, seals, and linings in the processing plants, proving indispensable to the war effort. This critical application gave DuPont the incentive and resources to overcome the manufacturing challenges. After the war, DuPont registered the new material under the brand name Teflon in 1945. While its industrial applications continued to grow, its journey into the consumer world was slower. It wasn't until the mid-1950s that a French engineer, Marc Grégoire, used Teflon to coat his fishing gear, marveling at its non-stick properties. His wife, Colette, suggested applying it to cookware. This brilliant idea led to the first non-stick frying pan, Tefal, introduced in France in 1954, and later in the US in 1961. The rest, as they say, is history. Teflon's impact extended far beyond the kitchen. Its low friction properties made it ideal for aerospace applications, used in bearings, seals, and insulation for spacecraft. Medical science adopted it for implants and surgical grafts due to its biocompatibility. It found its way into plumbing, electrical wiring, clothing, and even architectural structures. Roy Plunkett's accidental discovery, a seemingly insignificant anomaly in a gas cylinder, evolved into a ubiquitous material that has fundamentally altered how we live, cook, build, and explore. It stands as a testament to the power of observation, the value of scientific curiosity, and the remarkable outcomes that can arise from pure, unadulterated serendipity in the pursuit of knowledge. The legacy of Teflon reminds us that sometimes the greatest discoveries are not found where we look, but where we least expect them.
Subscribe to the channel and hit the bell icon for more amazing videos.